Record. So I got one more of the previous Zooms loaded up to YouTube and successfully activated. So there's one more up there if you need to go back and view it. I'm still working on the next one. Like I said, there's always this, there's lag time problem. Questions about previous stuff we've done in this chapter. We've done a little history. We've done some isotopic notation. We spent a fair amount of time on nomenclature, of which we're going to finish up some tail end stuff today. Questions about the things we have covered? All right, we are going to go on a little bit of road trip. Okay, I'm a geek. I have a chalkboard in my household, which is on the wall in the hallway. So I'm going to lug my not cooperative sometimes webcam and laptop out to the hallway to see if I can show you some additional examples of some extra nomenclature stuff. But I think I'm actually going to cover the tail end, because we had one more section that we hadn't talked about yet, cover the tail end of that, and then go over and use my chalkboard, because it's sort of easier than using the whiteboard. I really hate the whiteboard function on Canvas in a lot of ways. So I'm going to finish the tail end, and then we'll kind of jump over and I'll give you some additional examples. See if my screen share cooperates. We are at the very end of the chapter. So the part that we did not get to last week was the part about the acids. So part of the deal with the acids, especially for this semester, is if you see a molecule that begins with one or more H's, providing it's not actually a molecule of water, it should be some form of acid. Now, a lot of the acids contain oxygen atoms. Some of them do not. But the difference between those two categories influences the way you name them. So if you look at a molecule and you say, okay, I think it's an acid because it starts with an H, but it has no oxygen atom in it, you can then use a prefix of hydro and a suffix of ic, I see. And I gave you two examples there. Hydrochloric, okay, stuff that's in your stomach, has one atom of hydrogen, one atom of chlorine. It's an acid, but it has no atoms of oxygen present. So this is part of the reason why we call it hydrochloric acid, because chloric acid is actually something different. Hydrocyanic acid, if it's dissolved in water, it's an aqueous solution. If it's in the gaseous form, this is one of the things where if you breathe it, you die. Okay, hydrocyanic acid is got the cyanide ion in it, the C linked to the N. Now, the other thing that is true about the acids when we're talking about the ones that do have oxygens is that you have to pay attention to what anion was part of the molecule. If we look at two different versions that have hydrogens and sulfurs and oxygens, and SO4 is the ion that goes by the name of sulfate. SO3 is the one that goes by the name of sulfite. But because the endings of your ions are different, when you change them into the naming for the acids, we go back kind of sort of to something that sounds like the old naming system, which is the ick and the us problem again. Sulfate becomes sulfuric acid. Sulfuric acid is very nasty, and I watch way too much CSI, or NCIS, and other related things. Sulfuric acid you could dissolve a body in. Uh, on the other hand, sulfurous acid is acidic, but its power is not much more than vinegar. You could stick your finger in sulfurous acid and not really suffer any damage. There's a big power difference there, as well as a naming difference. So that covers all the main rules. So like I said, we're going to go on a little field trip. I'm going to grab up my laptop here and lug it over to the hallway and see if I can use my chalkboard. And of course, all of this is not cooperating. All right, hopefully that's mostly viewable. So let me run through some examples. Because like I said, it's kind of easier to do this on the chalkboard than it is to do it on the whiteboard. So of the things that we've been doing for nomenclature, we had categories that involved normal metals and non-metals. So for instance, we could do K2S, okay? And knowing that this part is your metal, your K, and your sulfur is your non-metal. It's also not a transition metal, so we don't need any Roman numerals here. If we name this, we're going to call it potassium sulfide. Okay, that way you have the IDE ending that is true to indicate that this is your anion part, and then you have the name of the metal for the front end there. All right, so if we have something that is a transition metal, let's start on one of the ones that doesn't have a polyatomic first. If I do CrCl3, okay, these are the ones where you kind of have to start over here on the right-hand side and work your way backward to the left in order to figure out what the Roman numeral is that's going to go with your metal name. So I know that it's chromium. Okay, I don't know what the Roman numeral is yet. I'm going to look at my chloride. Chloride is a halogen. So I have -1, and there are 3 of them. So that's 3 negatives. This would indicate, because this must be a neutral molecule, that my chromium needs to be a 3 version. And then we've still got to use the end there that has the indication that it's an anion. So we've got chromium 3 chloride. We also did some versions that had polyatomics. So let's see, let's pick on one that's, I'm trying to decide which one I want to use. How about NaOH? This is something you're going to see off and on in lab for the duration of the semester. The OH is a polyatomic.
So it has a one-word name. It also has a single charge to it. So we've got sodium hydroxide. And I messed up my X. So name of the metal, name of the polyatomic. What if you have messier ones? Here's one that is a little more challenging. V for vanadium. And then the C2H3O2 is one of the ways that you can write acetate. So I've got vanadium. In this case, I have two acetates. Acetate has a -1 charge, so this needs to be vanadium 2 acetate. Let me do one more down here at the bottom. That's one of the acids. So HBrO2. So you're going to have to look up the latter half here. This is known as bromite. So ending in the ITE for the ion part, the anion part, we only have a single hydrogen out in front. Bromite is going to become bromous acid. Don't call it hydrobromous acid. Hydro would imply that there were no oxygens at all. Hypo would imply that there is only one oxygen. So all of these are, look at the symbols, figure out your names. However, you must be able to go in both directions. I usually refer to the other one as the backwards direction. And statistically speaking, people have more problem with this. Looking at the name and figuring out what the formula is. Okay. So if I have, let's do barium bromide. You don't only have to think about what elements are being represented, you also have to think about the how many. So let's kind of do a little note taking underneath here. So barium is in the second column of the periodic table, known as the alkaline earth metals. Bromine is a halogen. Bromines like to be -1. So look at your charges. This one's +1 and this one's -1. You need 2 bromines in order to actually have a neutral molecule. So when I write this as a formula, it becomes BaBr2. Do not write the charges into the molecule as your finished answer. Once they have combined, all of your cations are canceling out all of your anions, and there are no leftovers. This is why they're not displayed in the molecule. How about manganese or I want to use sulfate. All right, manganese. Manganese is Mn, and in this case, pay attention to the Roman numeral there. This is Mn +4. Sulfate is SO4 -2. Okay, again, now you got to think about the charge end of it. I've got 4 positives, and at the moment I only have 2 negatives. I need more than 1 sulfate. When I combine this, and write this in my formula, I need to put parentheses around my SO4, and it then also needs a subscript of 2 on the outside. That way, you're making sure that you have enough negatives to cancel out your positive. How about one that has no metals? Okay, we talked about one of the categories as being ones that have no metals at all. We could do sulfur, tetrachloride. And one of the weird niceties about non-metal containing molecules that have no metals at all is we actually don't have to worry about the charges. We just have to worry about the prefixes. So sulfur, I'm going to have a single S, but tetra is my indication that I have 4. So I am going to have SCl4, excuse me, as my molecule for that. How about acids? Hypochlorous acid. So hypochlor is going to tell me that I have OCl. How many Cl's do I have? Okay, look at your OUS. So hypochlorite became hypochlorous. Conjugate your anions. And I'm going to put an H on the front because hypochlorous or hypochlorite has single negative charge, so I only need 1 hydrogen to make this work. As I said, statistically speaking, people find starting with the names and going back to the symbol versions more difficult. You really, really have to pay attention to your charges when you are doing this. All right, so that is the end of chapter 2, and I'm going to lug you back over to my desk. All right. Put on my glasses so I actually can see at this distance. All right, so that is the end of chapter 2. That also means that that is the end of the information for the first test. I'm going to give you just a few hints at this point, but I will talk more about the test on Thursday. So things to consider, okay, 2 chapters. So all the things we covered for chapter 1, all the things we covered for chapter 2. Your homework, as well as the notes, are the biggest key functions for needing or deciding what you need to understand in order to be able to do the test. The test is obviously, because we're still on Zoom, it is a Canvas-based test. You need the lockdown browser, but I don't do the camera thing because lots of people do not have enough bandwidth to do the test and stream the camera thing at the same time. We had problems with that in the past, so I only use the lockdown browser part. Another thing to consider, and this has become sort of a college-wide thing, is if you have Apple products, some of them do not interface well with the lockdown browser. And also, Chromebooks are problematic
because they are based upon the Android system. Basically, they don't operate in their internals. You can tell I don't know like all the details about this, but they don't operate on the same kind of operating system that a traditional laptop does. They have a more Android, like cell phone based system. So the Chromebooks do not appear to interface with the Canvas system for test taking purposes. Keep that in mind. Your test is coming this weekend. So 2 tests. There's going to be a mixture of problems on the test. Some of them are multiple choice. There's some true false. There's some definitional stuff. There's problems too. And there's naming, okay? Because naming was part of chapter 2 stuff. Also, because I'm doing the test on Canvas, I'll call it my methodology for question design is different than if you were taking a paper test. You have a 4-hour time block. Once you start the test, it basically starts the timer. Okay, so keep that in mind for what day you want to take the test. I will set it to go live basically a minute after midnight on Friday. And it will lock down at midnight on Monday. So you have a 4-day window, because I know that there are lots of people. I've got military students. I've got people who work healthcare jobs that often have kind of odd hours in terms of weekends and things like that. So this is why I give you a 4-day window. But once you start the test, you only have 4 hours to do it. Some of the test questions are a little more extensive because you are allowed to use your notes and your textbook and your homework. You just can't surf on it. Okay, you can't like go on the browsers and look stuff up. But there is no memory per se involved. This testing version is based more upon understanding. So questions about, like I said, I'm going to talk some more about this on Thursday also. All right, so homework then, since we've now finished chapter 2, homework will be due on Thursday. I will set the homework due date for basically midnight, 11:59 on Thursday. And then on Friday, I will post the answer key so that you can view the answer key for your chapter 2 stuff. I might not have them graded yet, okay, but obviously you're not turning in physical papers to me for your homework. So you will still have your whatever you did, and you can then compare it to the answer key and see if you made errors. So that's currently my game plan. Since we only have 10 weeks and not 16, usually I try to backtrack it a little bit more, but if I push the test off, it's going to make me have to give it in the middle of a week, which I know for a lot of people is way more problematic. So this is why I'm trying to confine test dates primarily to weekends. Anybody have like weird scheduling problems that you know are going to come up this weekend? All right, onward. Let me find my chapter 3 notes. Okay, and share. Okay. Okay, we're gonna kind of veer back in the other direction to some degree. We did a lot of math things in chapter 1. We did kind of more conceptual and nomenclature things for chapter 2. There's a little math there in the middle. But we're going to now kind of veer back in the other direction, back toward more calculation end of things for chapter 3. So one of the things that is, I'll even say somewhat true. How do you count something you can't touch? Think about this in terms of, unless you have a handy scanning tunneling microscope or atomic force microscope, you can't touch an individual atom. So think about, like, especially they run these around Halloween time often. Guess how many M&Ms are in the jar? Guess how many lollipops are in the jar? Well, what if you actually had a little bit of additional information? What if you knew some things about that scenario? What if you knew the average mass of an M&M? And what if you knew the total mass of the jar? We're making kind of an assumption here that they subtracted away the weight of the actual jar. I know that strawberry season was a few weeks ago, but if you go to the Virginia Beach or Suffolk or whatever strawberry patches, you take your bucket and they weigh your bucket empty, and they put a label on it, usually with a piece of masking tape that tells them how much the bucket weighs. And then when you come back with your bucket full of strawberries, they subtract away the weight of your bucket. We're kind of operating on that scenario. So let's say each M&M weighs 1.23 grams. This is an average. And all of them minus the jar weigh 358 grams. So assuming that there aren't any weird mutant ones or broken ones, we could probably get a pretty close estimate based upon this data. We could take the 358 and divide by your average one, and I get something that's not quite exactly a whole number, but I can round it and say that there are probably 291 in the jar. I'm using the data to reach this conclusion. So we're going to return to the unit that we mentioned kind of in the middle of chapter 2, which was AMUs, atomic mass units. One of the things we said was they are 1/12 of a carbon-12 atom. We're referring to the specific isotope. Now, most elements have at least a couple of isotopes. Some have more than a dozen. So one of the things I did here was I looked up tungsten's isotopes, and there's actually, like, I think 11. I fiddled the data a little bit to make it a little bit more manageable problem as an example. So we're going to say that tungsten has 5 isotopes: 180, 182, 183, 184, and 186. One of the things we mentioned also in chapter 2 is when they report the atomic mass as a decimal number on the table, what they're doing is giving you a weighted average. So we're kind of rehashing a little bit something that was introduced in the previous chapter. I'm going to take the atomic mass and I'm going to multiply it by my percentages, keeping in mind that I have moved my decimal place 2 spaces on my percentage. So if I multiply 180 times 0.0012, I will get 0.216. If I multiply 182 times 0.263, I get my 47.866. And then look on further down the line, I get 26.169, 56.488, 52.08. One of the things that is always true in weighted averages is there is no division step. You are multiplying known values times percentages, and yes, you're doing a little decimal place moving. But once you do those multiplication steps, then you are totaling the answers from those steps. Do not divide, okay? I know there's 5 isotopes. Don't go back and divide by 5, okay? That's not the way this kind of math works. The AMUs are really great. If we're talking about 1, 2, half a dozen atoms, our balances, since everybody's been through lab at this point, are ones that use a balance that only reads to 3 decimal places. You're not going to be able to weigh AMUs directly. That our balances definitely don't go that low. Instead, we use grams and moles. So if you're in biology, the mole is a little rodent-based thing that probably digs holes in your front lawn. A mole in chemistry is a word that represents a number, okay? Think about this like in terms of, English has collective terms, okay? If you say, I have a dozen, doesn't matter whether we're talking about eggs or bagels, if you tell somebody that you have a dozen, they know that in English that word represents 12. If you go shopping at Office Max, it is possible to buy a gross of ink pens, 144, or a ream of paper, which is 500 sheets. So mole is that kind of a collective word. They arrived at this by saying that it was the number equal to how many carbon atoms are in 12 grams of carbon-12. The number is 6.02214. We usually don't pay a whole lot of attention to those last 2 decimal places, times 10 to the 23rd. All right, to give you some ideas. If you had a mole of mini marshmallows, like they come in the hot chocolate packages, if you had a mole of those mini marshmallows, you could make a line from here to the planet formerly known as Pluto and back about 7 or 8 billion times. If you had a mole of water droplets, you could take a shower for about 3 trillion years. But also, if you have a mole of water molecules, you have 15 milliliters. Some of you did lab yesterday. Some of you are doing lab tomorrow. A couple of people, I think, have Mr. Seniak and are doing lab either Tuesday or Thursday. But anyway, this week is the lab that we are doing separation of mixture. One of the things you must measure out to put in your evaporating dish such that you can dissolve the salt away from your water is 15 milliliters of water. Okay, we used graduated cylinders in the previous lab. We used graduated cylinders. We were determining the volume of your little metal chunks. for doing the density. So you have some idea what 15 milliliters represents. When we look on the periodic table, we're going to make double use of the atomic masses. We mentioned iron before in the last chapter as having an atomic weight of 55.85. That also means 1 mole of iron weighs 55.85 grams. Lead's much further down on the periodic table. 1 atom of lead weighs 207.19 AMUs. 1 mole weighs 207.19 grams. As I said, we are making kind of multiple uses of the same number value and changing out the units. You need to be able to convert back and forth between these different kinds of units. And I have some examples here, and there are some more in your textbook. If I want to find out how much 0.38 moles of aluminum weighs, start with your given information. Look up the atomic weight of aluminum on the periodic table, 26.98, and set it up as a conversion factor. It is 26.98 grams per mole. Multiply those two together because there's a mole on the top next to my aluminum symbol, and there's a mole on the bottom, 26.98. Okay, that the moles cancel out. You're going to multiply your two numerical values together, and you got 10.252 grams of aluminum. Now, I didn't pay critical attention to my sig figs here. In part, I'm striving to make it resemble lab data to a degree, to try to get you used to the idea of when you are recording masses in lab, you need to record all 3 decimal places, even if the last one is a 0. And so even though according to the rules of sig figs, I should actually round this slightly and call it 10.25 grams and not have that final 2. I went ahead and left it unrounded so that it would resemble lab data. What if you're going back in the opposite direction? How about if you know grams, but you need to find moles? The math is similar, but your conversion factor is reversed. I have 20.4 grams of barium. Look up barium on the periodic table. It's 137.34. But because I want my grams to cancel out, I am going to put it on the bottom and put my 1 mole unit on the top. Divide 20.4 divided by 137.34, and I end up with 0.149 moles. Sometimes you need to go from grams to atoms or back. It has to be done in 2 steps. Now, it is up to you whether you want to link those two steps together or if you want to do it as 2 separate steps. I did it as 2 separate steps here in my example. I started with 2.89 grams of gold. Look up gold. Gold's pretty heavy, 196.967. So my first step is the conversion from grams to moles. Divide, and I end up with 0.0147 moles. And then I pulled that number down into my second step. I know by definition how many items, in this case atoms, are in 1 mole. And so I could, and I did not do this, and perhaps I should have, put my word in here. Okay. 0.0147 multiplied by 6.02 times 10 to the 23rd atoms gives me a really big number. Okay. I get 8.83 times 10 to the 21st atoms. Something to kind of keep in the back of your mind. Even if you had a couple of milligrams of an element or compound, you're still probably going to have a few trillion or more atoms or molecules. You will almost always end up with a number that really has to be written with an exponent when you are giving the answer for how many atoms or how many molecules. So we are digging deeper into utilizing all of this information. So those 3 examples involved doing the calculations for just an element by itself. We need to also then be able to do a similar thing involving a molecule. Now, if you look at your text, if you look at your lab book, if you are looking for extra examples to study from on websites, there are 3 different terms which all basically mean the same thing. Your textbook tends to be fairly consistent about referring to it as a molar mass. Some of the previous textbooks that I was really fond of were more likely to use the term molecular weight, but you also might see the term formula weight. On an undergraduate level, they all mean the same thing. How many grams in 1 mole of a molecule? So I'm going to teach you a method that, using the method, streamlines the math for the other variations that you have to be able to do. Look at my big chunky molecule here. I've got Fe2SO43, lots of elements, a whole bunch of different atoms. So the first thing I did was I made a list of the elements. I wrote Fe, S, and O for oxygen. Then I went back and I counted them to make sure I was keeping track of the right number that were in that molecule. I had 2 irons. I had 3 sulfurs, because the 3 on the outside affects everything inside the parentheses, kind of like algebra. And I have 12 oxygens. So list your elements, then figure out how many you've got. Excuse me. Then periodic table, look up the masses of those elements. So iron, 55.847, sulfur, 32 and change. And I use the rounded version of oxygen. Some of the periodic tables you will cite the unrounded version of iron as 15.9994. for purposes of most math problems, it won't make enough difference to change your answer. And then I multiply across how many times the mass gives me a number. So for my iron, I have 111.694. For my sulfur, 96 and some, 192 for my oxygen, and then I totaled them. Note, there are some similarities in the way the math is done to when we were doing the weighted average problems. This is a big molecule. If I had one complete mole, it would weigh almost 400 grams, in part because it's a really huge molecule. So all of those things are going to kind of continue in terms of how we utilize the information, okay? And setting it up the way I have it kind of lined up in rows, and then the rows kind of progress across in the math. Like I said, there's a reason for doing this. It streamlines and makes a little bit more straightforward some of the other things that we were going to do with that information. So let's take about a 10-minute break. And we'll come back and do a bit more of chapter 3. We're definitely not getting through the end of all of chapter 3 tonight, but I want to get a little bit further in it, so that when we spend some time talking about the test on Thursday, that we still have some time left over to work a little bit more on chapter 3. So I'll see you guys in about 10 minutes or so. All right, I'm going to switch gears for just a minute over to lab stuff, just as a reminder, because there was some confusion about the version of the lab book, partly because Baran, which is listed as the author of the lab book, has been producing lab books since I started teaching for TCC in the late 80s. So there are many editions of the lab book. This is the one that you are supposed to have. I have heard, we'll call it unconfirmed rumors, that the Barnes & Noble in MacArthur Mall, which is supposed to be the source where you can get them, supposedly is out of stock. And I don't know why. But that
Yeah, I
is,
actually went there yesterday, and
did
I
they actually
found out
have
it
any?
was out of stock. Yeah. No, I went and I asked them. I was like, "Do you have any of these books?" They said no, but they said like they're gonna order some, but I don't know when. They said they're gonna order some maybe in a week, or it might come in a week or two. So
I don't know why they do this to us.
I got mine
It's
at
like,
the Virginia Beach one, like a week ago.
I was gonna say, does the beach campus have them at all?
I don't know if they have them now, but I got mine like a week ago and they had it.
Might be worth a phone call to the other campuses then to see if they actually have any in stock. But it says Norfolk only, and it has to have this picture on the front. It has to have like, the multicolor glassware on the front.
Yeah.
There's been a whole bunch of different versions over the years. I don't have some of my old ones. Usually, sometimes I leave the old ones stacked next to my desk, but it has to be this version, because otherwise it doesn't have separation of a mixture, and it doesn't have the metathesis lab. And then if you take 112, which is also from the same lab book, the other versions don't have the heat of the enthalpy of vaporization lab that are all part of this particular version of the printing of the lab book. So yeah, I would say maybe phone call the other campuses, see if anybody else has them in stock. That's about all I can suggest right at the moment. You'd think, it's like, we haven't changed lab books in like 2 years. So you'd think that they'd, order them and just know that they're going to use them the next semester if they don't sell them all out in one go. Yeah, it's kind of complicated. Okay, so if you have a lab book, or you have the printouts from Dry Lab 1 and Experiment 1, here are some other reminders. Okay, because part of this is actually loaded to Canvas. So Dry Lab 1, okay, if you have a lab book, the pages have a gray edge to them. And I know that there was some confusion as to what pages you turn in. Okay, the first page you turn in should look like this. Okay, there should be 6 total pages. So there's this page that's all multiple choice, basically. There's also this page, which is kind of a mixture of a little short answer, some true false stuff, and a little bit of math down at the bottom. There's a picture, the page that has pictures on it of, there's a basketball hoop, there's a hurricane, and there's a beaker down here in the far corner. The back of that page also has more pictures on it. Railroad tracks, coffee cup, all the way down to these big stone pillars, okay? And then there's the part we did in lab, which also has 2 sides to it, okay? So it has the front side, which is where we originally recorded the data, but then there is also the back side of that, which has 3 calculation problems. So when you get ready to turn it in, whether you turn it into me digitally or if you turn it into me on Canvas, you should be turning in 6 pages, 3 pages back and front, okay? And they have this bizarre numbering system. if you're looking at the little tiny numbers, as opposed to the bold numbers that are also on printed on the page, it's pages 55 through 60. That's dry lab 1. When you do experiment 1, be aware that there is a pre-lab that you do need to eventually do that has its own separate page here. Okay, it's basically read the data, answer the questions, and do the math. It also has a back to it. And then this is your report page that we used in lab. And some people I know I gave copies out to, and it's also loaded to Canvas. And then the back of that page has data, and there's kind of a white space in the middle. You don't need to do the class data stripe here that's in the middle. And then I assign, if you have lab with me, I assign 2 of the questions, numbers 1 and 4. So that one is a back and a front for the pre-lab and a back and a front for the lab report. So most of the things you turn into me have at least 2 pages. Some of them have more, but kind of keep that in mind when you're either scanning things or taking pictures, that you need most of the things you're turning in from me to lab have multiple pages involved. Because I had a couple people turn in stuff to me digitally that did not have all the pages. So that's why I was kind of figured maybe I should talk about that a little bit. I am utterly frustrated that the bookstore didn't even order. I mean, let's see, I have 15 students in lab. I know that Mr. Siniak has no more than 20. And I think Mr. Wheaton only has 11. It's like, they should have ordered 50 copies minimum. So yeah, I'm not really sure what's going on with that. I will see if I can talk to Mr. Wheaton tomorrow and see if I can, I don't know if he has any pull for getting them to order stuff faster, since he is higher up the food chain than I am. So any other lab questions while we're talking about lab stuff? So this week, both the Monday people and the Wednesday people, and if you have somebody who is not me for lab, we are all doing the same lab this week, which is called separation of a mixture. This is time-wise one of the longest labs in the semester. It often takes the full 2 hours to get the information presented and then to actually do all the steps in the lab report. So this is definitely one of the longest ones of the semester. All right, back to molar mass. All right, next one up. One of my favorite molecules, caffeine. Caffeine is an organic molecule that only has 4 elements in it: carbons and hydrogens and nitrogens and oxygens, in somewhat ring-shaped structures. I probably should have gone to find a picture of the actual structure of a caffeine molecule. But I'm using the same method to start this problem. I looked at how many of each element I had. So 8 carbons, 10 hydrogens, 4 nitrogens, 2 oxygens. Then I did my step that involves looking them up on the periodic table. 12 for carbon, slightly over 1 for hydrogen, a little over 14 for nitrogen, and 16 for oxygen. Again, do your multiplication across as your next step. So 96, 10, 56, and 32 essentially gives you a molar mass for the molecule of 194.2 grams per mole. I want to find out a cup of brewed coffee, not the nasty Keurig crap, an actual brewed cup of coffee. How many molecules of caffeine are in an average cup of coffee? So I did this in a couple of steps. I just suddenly realized one of my numbers is squished off to the side a little bit. All right. First thing I need to do is convert from milligrams to grams. We know that there are 1,000 milligrams in a gram. All I did was move my decimal place from 300 to 0.3. Then I used the number that I calculated above, which is my molar mass. Put it on the bottom because we are going from grams to moles. Do my divide. 1.55 times 10 to the negative third. If you didn't write it in scientific notation, it wouldn't make a difference mathematically. And then I did my additional step of multiply my moles times my Avogadro's number, 6.022 times 10 to the 23rd. So a cup of coffee gives you about 9.33 times 10 to the 20th molecules of caffeine, roughly 1 molecule for every cell in your body. All right, what if we take this methodology and this information and we kind of undo it? Instead of using it to figure out how much a mole weighs or a part of a mole or that sort of thing, what if we use it for more analytical purposes? So if you take the atomic mass of one of the elements, if we were doing it for the caffeine molecule, we might maybe pick on carbon, and you put it over top of the molecular weight for the whole molecule, and then we multiply by 100 so that it is not a literal flat fraction, so that it actually looks like a percentage. But you may see them referred to by any one of these 4 different terms. Again, your textbook may not match your lab book in terms of which word phrase they like to use. You might see it called mass fraction. You might see it called mass percent or percent by mass. You might see it called weight percent. So we're going to use some of the same sorts of math and a little bit of a tinker in that we're going to add some multiply by 100 to it in terms of analysis. All right, let's pick on silver sulfate. So silver sulfate has 2 atoms of silver, 1 of sulfur, and 4 of oxygens. As I said, there's a method to why I set up my figuring out what my molar mass is a particular way, because it will save me a step later. So look up your masses on the periodic table, and I didn't write one here for the sulfur because there was only one. I just wrote the number on the other side of the equals. So we've got 2 times 107.87 for the silver. That gives you 215. Sulfur is 32. 4 times 16 gives you 64. This is a moderately big molecule. It has a molar mass of 311.804. But look, I've already done part of the math that I need for the next steps. So the 215 that I multiplied across, I can pull down and dump on the top when I am calculating what my percent of silver is. I've already done the multiplication step of the fact that there are 2 atoms times the 311.804. Do your division, multiply by 100 so it actually looks like a real percentage, and I get 69.19%. For my sulfur. Now, sulfur only had 1 atom anyway, so I'm just going to use the 32.064. The bottom does not change. It remains the total 311.804. Divide, multiply by 100. I get a little over 10% for my sulfur. And the last one, I have 64 over the 311. Divide, multiply by 100, and I get 20.5%. Now, if you add up all of the percentages for all of the individual elements in your molecule, you should get 100, or in this case, approximately 100. I did a little bit of rounding when I did my divisions. This is a double check step. Once you have done the division and the multiply by 100 step, adding all your percentages together, if you don't come out with at least something awfully close to 100, part of that is your tip off that there's a math error. Okay, if I added up my 3 values and I came up with 85%, I glitched something somewhere. Or I forgot one of the elements. It's a way to try to make sure you are minimizing any math errors that might occur. So have a look at this one. This one is similar. I kind of streamlined the steps a little bit here. I've got potassium chlorate. ClO3 is a chlorate anion. I've got 1K, 1Cl, and 3 Os. I didn't show you all the steps here. Okay, I didn't show you that oxygen is 16. So 3 times 16 is where the 48 comes from. My molar mass, and I'll go back here and put a unit in just to kind of make sure I'm what did I do? I'm glitching my lines there. All right, so it's 122.6 grams per mole. I put each of my individual element totals over the molar mass, multiplied by 100. This one actually had more, I'll call them more similar values. I've got 31.9 for my potassium, 28.9 for my chlorine, 39.2 for my oxygen. It all basically totals up to about 100%. What if instead of percentages, we wanted to analyze things from a more ratio-oriented point of view? So more buzzwords. Empirical formula versus molecular formula. So, okay, think sort of fraction theory for this. Empirical formula is the ratio of the types of the atoms in a molecule in smallest whole numbers. Okay, if I have 5/10 of something based upon math, I can reduce that fraction down to 1/2. 1/2 being the lowest terms. That's kind of what the empirical formula is doing for you. Now, the molecular formula is the exact formula. So if I have 5 yellow golf balls and 10 white golf balls, and I actually have 15 total golf balls, then okay, the ratio is useful, but it doesn't actually tell me the full set of information. Just saying I have a 2-to-1 ratio doesn't actually indicate to me that I have twice as many of one color as the other color. So molecular formula tells you exactly what's in the molecule. So let's look at C6H6, and I'm gonna draw a picture here for you on the whiteboard. Just because this is an important molecule and we will come back to it again later. Where's my draw function? All right. So C6H6 looks like a little hexagon. And it has carbons at each corner. And we'll go back later and talk about double bonds. And every carbon on the wheel has a spoke that is a hydrogen atom. And so it looks kind of like this jagged little wheel that has all these little branches poking out from it. And all those branches are hydrogens. So this is known as benzene. I'll spell that for you. Benzene. All right. And its formula that we just saw was C6H6. Okay. This not only plays a part in as a really good example in certain things that we encountered this semester, it again shows up again in second semester if you take 112. So I figured it would help to give you a little bit more of a idea on what it is we're actually talking about there. So 6 carbons and 6 hydrogens, that's your molecular formula, because that's how many total are there. But if we do that least common ratio idea, its empirical formula is CH. 1 carbon for every 1 hydrogen. Remember that normally the ones are not written, they are implied. How about something that has a few more elements involved? C12H4, Cl4O2. One of the things that you kind of see there is that all of my subscripts are even numbers. So I could actually go back and divide them all by 2 and have a more stripped down ratio, the left one being the molecular one and my empirical one being C6H2Cl2O, 1 single O. Why would we want to do things like this? Part of the reason for this is it allows you to analyze compounds in a lab situation to get some basic information about how many of one element to how many of another element. And I picked on lead and chlorine. One of the things that we just finished up in the nomenclature section is looking at lead and noting that lead comes in two versions because it is a transition element. It comes in a +2 version and a +4 version. So I have a sample, and I know that my lead weighs 0.6884 grams. I know that my chlorine weighs 0.2356 grams. They make a binary compound, so the two of them stick together. I want to figure out what the empirical formula is. So I'm, again, doing this from a kind of analytical point of view as opposed to just doing a molar mass alone. I'm going to take my grams of lead, divide by its table weight, and I have 3.3 times 10 to the -3 moles of lead. For my chlorine, same basic premise, 0.2356, divide it by its atomic weight from the table, 35.45, and I get 66.6 times 10 to the -3. This one's a little bit obvious, and you can kind of eyeball it and go, oh, 6.6 is twice as much as 3.3. Both of them are to the -3. If you wanted to look at it from a math point of view, then you could put the big one on the top and the little one on the bottom and go, oh, I have a 2-to-1 ratio, which is a way of determining that I have PbCl2 as my compound rather than PbCl4. All right, so we've covered a chunk of chapter 3. I know a few people have already turned in their homework for chapter 2. If you have not turned it in already, you should finish it and turn it in tonight by midnight. Like I said, actually, no, okay. I glitched that. We finished chapter 2 today, so actually homework is due on Thursday. But feel free to turn it in earlier if you have it done. And I will post the answer key on Friday so that you can review it before you take the test. So test upcoming for this weekend, chapters 1 and 2. Okay, fairly large chunk of information, but summer semester is always faster anyway. We have the next test is 3 and 4. Then we have 9 and 5 as the third test, and 6, 7, and a smidge of 8 as the fourth test. And then there's a final exam. So homework is an ongoing thing. Homework is part of your key, though. Homework is a real, if you plow through your homework and understand, even if you glitch it when you are working on it, if you understand where you went wrong, that is a key piece to making sure you have a grasp for the material for the test. Questions? And yeah, I don't have any really super great solutions regarding the fact that the lab books are not where they're supposed to be. Call the other campuses on the off chance that they actually have some in stock. I don't know. Questions? Lecture stuff or lab stuff?
No, I don't have any.
All right. Otherwise, I will see some of you tomorrow night.
Okay, thank you.
Get them out.
Thanks.